All right, I think we're live. All right, welcome to Mr. Linford's math class. Today we are going to be kind of doing a similar thing that we did to the morning live stream where we review some problems from section 10.7, which we had last week, solving radical equations. Then I'd like to get into more of a talk about section 11.1, what you were assigned today, which is solving quadratic equations using the completing the square method. First off, let's start with the section 10.7. If you have any questions or comments or problems you'd like me to review, please let me know. You can let me know over in the live chat. I will be going over the second problem from the exit ticket that was assigned today as well. But let's start with section 10.7 first. Notice that this is a radical equation because we have a radical in there. Now the trouble is we have to isolate the x variable, but we can't get at the x variable when it's trapped in the radical. So what we have to do is get rid of that radical somehow. So let's first isolate it. So I'm subtracting 3 from both sides, and we end up with the square root of 2x minus 3 equals 3. Now that we've isolated the radical, what we have to do is we have to get rid of it. The way to get rid of the radical, the square root, is to square both sides. So the only way to get rid of a radical is to raise both sides to the power. That gets rid of it. So instead of a square root, let's square everything. We end up with the 2x minus 3, and that's equal to 9. Now, you'll notice that when I squared both sides, I said raise it to the power that gets rid of the root. So if this was a cube root problem, I'd raise both sides to the third power. If this was a fourth root problem, I'd raise both sides to the fourth power, etc. Now let's try this problem. A little more complicated, but not too bad. Again, we got to get at the a. Notice that there are multiple a's in this problem. So how do we access them? How do we combine them together? Again, the trouble is that this a is trapped inside of the radical. So I want to get rid of that radical. I have to before I can do anything with this. So I'm going to have to square this. That's the only way to get rid of the radical. Now, if I square both sides right now, this is going to become very, very messy. So instead, what might be a nice alternative was, again, to isolate the radical, get it by itself. So let's add 2a to both sides. My stylus will work. Let's add 2a to both sides. And we'll end up with 2 times the square root of 6a plus 7 equaling 2a. And you know what? Let's go ahead and divide both sides by 2. We'll end up with the square root of 6a plus 7 equaling just a. All right, now we want to go and square both sides. So let's do that. The square root of 6a plus 7 squared and a squared. Well, the square root and the exponent cancel out, so we're left with 6a plus 7. And then here we have an a squared. Now, hopefully you're saying to yourself, okay, we've gone through and we've canceled out all the radicals, so now we can solve the equation. And hopefully you're saying to yourself that this being an a squared means that we have a quadratic equation. This is how we have to solve it. We have to get all of the terms to one side, and now we have to solve it by the zero product property. We have to factor this down. When you have quadratic equations to solve, you need to solve them either by the zero product property, or as we learned today, you could complete the square with this. I'll do zero product for right now. We're going to factor it down to 2 binomials. And let's think, what multiplies to get us -7, but adds to give us -6? I'm thinking -7 and +1. So set each of these factors equal to 0. And let's say that a could be 7 and a could be -1. These are our 2 solutions to the radical equation. Now, we are not fully done yet. We have the solutions for both of them, but the trouble is that we solved a quadratic equation to get these solutions. A quadratic, as a function, has an infinite domain, right? It goes from negative infinity to infinity. Our issue is that we're using this infinite domain function to solve something that doesn't have an infinite domain. This huge radical problem up here doesn't have an infinite domain. It's restricted. Remember, when we had square root problems, their domains were restricted. They only started at a certain value and continued on. So we might have error solutions here. We might have what are called extraneous solutions, things that solve the quadratic but didn't actually solve our problem, things that might have solved the quadratic but were outside of our domain for our problem. So we have to check our work. That's the struggle anytime we work with the rational or fraction equations or the radical root problems. You might have extraneous solutions because you're converting something that has a restricted domain to something that has an infinite domain. So let's test them. I'm going to first test 7, so I'll plug in 2 square root. 6 times 7 is 42 plus 7. And then I'm going to subtract 2 times 7, which is 14. And I want to show that that equals 0. And then the other setup is going to be 2 times the square root of, okay, negative 1 times 6 is negative 6 plus 7. And then minus 2 times negative 1, well, that's just plus 2. I want to show that that also equals 0. So let's get to solving. 2 times 42 plus 7 is 49. So I have root 49 minus 14 equals 0. The square root of 49 is 7. So 2 times 7 minus 14. And what do you know? 2 times 7 is 14. Minus 14 gets me 0. Yeah, that works. Okay, so 7 is in fact a true solution to this problem. It's a true solution to my original equation. Now let's test negative 1. 2 times the square root of, well, negative 6 and 7 is positive 1 plus 2 equaling 0. The square root of 1 is just 1. And if I multiply that by 2, I get 2 plus 2 equals 0. That doesn't work. So this is going to be extraneous. I'm going to say it's an extraneous solution, meaning we did all correct work to find a solution for the quadratic, but it didn't actually work for the radical. So that's the issue here. When you're writing your answers on the tests, I'm fine if you write both solutions, but you would have to list one as extraneous. So on tests, I'll usually just say, tell me the solutions that are non-extraneous. So I just say, just give me the number 7. But if you give me both, just make sure one of them's labeled extraneous or not, so I know that you checked your work. Let's try another problem. This time, this is problem 12 from the independent practice and problem 8 from the advanced practice, by the way. Let's try this one that has multiple radicals within it. Again, if you have any questions that you'd like me to go over, please let me know. Or if you want me to slow down or re-explain anything, let me know as well. We have a live chat going on to the side here that you can comment in. All right, when we have two radicals, again, our goal is to get rid of them. And the only way to get rid of them is to raise both sides to an exponent. So here we're dealing with square roots, so the only way to get rid of square roots is to square both sides. Now, we could do that, but this, when I FOIL that, it's going to be pretty messy. So again, it's sometimes nicer to isolate one of the radicals. Get one of these by itself. And what I always say to do is get the one that has the bigger radicand or the more complicated radicand by itself. You'll see why in a second. So of these two, it looks like 2x plus 3 might be a little more complicated than x plus 1. Just my opinion. So what I'm going to do is I'm going to isolate that. So I'm going to subtract over the square root of x plus 1 from both sides. So we end up with the square root of 2x plus 3 being equal to negative root x plus 1 plus 1. Okay? Now let's go and square both sides. If we square both sides, notice that the left-hand side, the root and the 2 just cancel out. So we're left with a 2x plus 3. That's why I said leave the more complicated one isolated, like leave it by itself on one of the sides, because when you square it, you don't have to do anything other than get rid of the root. So that takes care of the complicated one. The right-hand side, however, is going to require us to FOIL, or box method. So I'm going to set the box method up down here. I have the negative square root of x plus 1. Oh my gosh, my stylus does not want to work right now. And let's see, I got another root x plus 1, and it's negative, and a 1. All right, let's take a look at the first box right here. Negative times negative is a positive, and then the square root of x plus 1 times the square root of x plus 1 is just x plus 1. And then in the bottom corner here, we have 1 times 1, which is just 1. Now in the other corner boxes, we're going to have negative root x plus 1 and negative root x plus 1. So when I combine some like terms here, let's try to combine a couple things here. That's x plus 1 is x plus 2. And then let's combine these radicals here because they're like radicals. Negative root x minus 1 and negative root x minus 1 is negative 2 x plus 1. And that, I guess, is probably the best way of combining everything. We've combined all the like terms and the like radicals. So this is what we get on the right-hand side when we perform our multiplication and simplify things down. Now notice what we did here was we got rid of one radical, but we still have another radical to deal with. That's okay. When you have multiple radicals and you square both sides, you'll oftentimes just get rid of one. So how do you get rid of the other? Just do the same process. Just square again. So we're going to end up squaring both sides again. But first, let's go ahead and make it easier on ourselves. Let's try to combine some like terms. I'm going to subtract over the x, and I'm going to subtract over the 2. So we get an x plus 1 equaling negative 2 root x plus 1. Okay, so a little bit easier on ourselves here. Let's go ahead and square both sides. Now, sometimes people ask me, wait a minute, Linford, what about negative 2 here? Shouldn't you divide both sides by negative 2? We could. I just don't want to deal with fractions. So, I don't know. I'm just not going to do that. So I'll just leave it as is. So let's go ahead. We'll square both sides. And let's see what we get. Now the left-hand side, when we square it, again, going to have to do box method for this. We end up with an x squared, an x, and a 1. So the left-hand side becomes x squared plus 2x, x squared plus 2x plus 1, equaling, now the other side, we're just going to square each thing individually. Negative 2 squared, or negative 2 times negative 2 is positive 4. And then we have, instead of square root x plus 1, we just have x plus 1, because those cancel. So, take a look here. Again, this is a quadratic. It's a degree 2 polynomial. So, I'm going to have to solve this like I solve quadratics. That means let's simplify things down. So I'm going to distribute the 4 through to get 4x plus 4. I'm going to subtract 4x over. So I get x squared minus 2x. I'm going to subtract the 4 over. So negative 4 and positive 1 makes negative 3. So this is the thing that I am going to have to solve now. I have two methods. If you did the lesson for today, you know that you have the zero product property and this new property of completing the square. I'll leave the completing the square for later, so I'll do the zero product property for now. That says that I can factor this down and set each of the factors equal to 0. So what multiplies to give me -3 but adds to give me -2? I'm thinking -3 and +1. Now let's solve each of these. If I set each one equal to 0, I would get x equals 3 and x equals -1. These are my two solutions to the quadratic. So keep in mind, these are my solutions for the quadratic. Are they solutions also for the radical equation, the original equation I'm trying to solve? That's the trouble. We're going to have to test these. So let's see. Let's start with 3. The square root of 3 plus 1. Oh, that's just the square root of 4. Plus the square root of 2 times 3 is 6. 6 plus 3 is 9, equaling 1. Now let's test -1. We have the square root of -1 plus 1. Oh, that's just 0. That just cancels out. And then we have the square root of 2 times -1 is -2 plus 3, equaling 1. So let's see what we get. The square root of 4 is 2. Square root of 9 is 3. When I add those together, do I get 1? No. Doesn't work. So 3 here, I'm going to say, is extraneous. Not going to work. It does work for the quadratic, of course, but it doesn't work for the radical. Now let's test 1. The square root of -2 plus 3 is the square root of 1. And does that equal 1? Yes, it does. So x equaling -1 turns out to be the true solution for the radical. It does work, okay? Now let's move into section 11.1. If there are no questions about 10.7, I'd like to review the completing the square method. When we complete the square, it's a very specific process for solving radicals. I'm sorry, not for solving radicals, for solving quadratic equations, degree 2 polynomials. So the way in which we do that is we first have to make sure that this is in the correct form. And of course, my iPad wants to disconnect. Well, darn it. Tell you what, give me 5 minutes. I need to reboot my iPad really fast. And then I will be right back. So in 5 minutes, we'll continue our live stream. Just hang tight.